at this point, we've seen the definition of convergence for series. But in order to use that directly, we need to be able to take the nth partial sum and come up with an expression for it in what we call a closed form. If I can't take the limit as n approaches to infinity for my nth partial sum, then we won't be able to use the definition of convergence directly. So instead, in these cases, we'd like to come up with what we call tests for either convergence or divergence. And importantly, these tests will rely on the definition of convergence, but these will provide a different way that we can go about checking whether a series converges or diverges. The first one I'd like to talk about is the test for divergence. And I'd like to justify where this comes from based off of what we've seen so far. But before I get into that, I'm going to think about a little bit about logic. So to start with, though, I'm going to suppose that I have a series that I know converges. So the sum from k equals 1 to infinity of a sub k converges. Then what we can say is that by definition, we know that for the nth partial sum of this series, the limit as n approaches infinity of s sub n equals L for some finite L. So this also means that the limit as n approaches infinity of s sub n minus 1 is equal to L. So just to pause and think about that, what we're saying in our first statement is that as I send the subscript there, n to infinity, we know that the s sub n, the partial sums, approach this finite value L. So what we're doing here is we're still sending n to infinity. And here I have the n minus first partial sum. But importantly, as n approaches infinity, so too does n minus 1. And so we can see that this would have to approach and level off at that same value of L. So this is going to be a key thing to think of here. Now, why that's important, we'll see in a moment. Right here, if I want to now consider the limit as n approaches infinity of the nth partial sum minus the n minus first partial sum. Well, from our limit properties, that can be expressed as the limit of Sn minus the limit of Sn minus 1. At this point, we know that both of those limits are L, so we get 0. So what we want to come back to is considering what is the part on the left here. So if I were to consider Sn minus Sn minus 1. So Sn would be the sum of the first n terms, like this. And we're subtracting the sum of the first n minus 1 terms. So notice that much of this is going to cancel off. And in fact, everything in the second set of parentheses will be canceled with something in the first. However, this won't cancel. So because what we're deducing here is if ever I take subsequent partial sums, so the nth partial sum minus the n minus first partial sum, that always leaves simply the nth term of the series. So what this line above tells me is that, in fact, it's the limit as n approaches a sub n is 0. So that's the conclusion we can draw here. So putting that together, just specifically, if you think about what we were assuming and then what conclusion we could draw, we said that if we know that a sum converges, then the terms of that sum must approach 0. So this is what we just verified here. So notice that what we assumed there with convergence, we were able to bring in the definition that we know that the limit of the partial sums exists and is finite. And given that assumption, we were able to conclude that the limit of the terms, so not the partial sums here, the limit of the terms must be 0. So this is going to be a really important fact, and this is going to come up a bunch as we go through looking at different series. So we're going to practice with that a lot, but in particular, what we'll look at in a moment is that what we call the test for divergence is very much related to this statement, but it's worded a little bit differently. So here's where I want to think a little bit about logic. So this is, let's call this an aside on logic. So I'm going to make a statement here. Let's suppose that what I term A is going to be the statement that today is Monday. And statement B is going to be that the name of tomorrow starts with a T. And by the name, I mean like the day, Monday, Tuesday, etc. And then what we want to do is decide whether the following are true or false. So to begin with, the statement, if A, then B. So think about here that says, if today is Monday, then the name of tomorrow starts with a T. And that's true. If today is Monday, tomorrow is Tuesday. So we can verify that that's a true statement. The second one here is if B, then A. So that says, if the name of tomorrow starts with a T, then today is Monday. Well, that's false. So we say it's false if it's not definitely true. So, of course, it's possible that today is Monday, but today could be Wednesday. So we can't guarantee that that's going to be a true statement. Then I could say, if not A, then not B. So this is the statement, if it is not Monday, if today is not Monday, then tomorrow does not start with a T. And again, that too is false because today could be Wednesday. And then finally, the fourth statement, if not B, then not A. And that says, if the name of tomorrow does not start with a T, then today is not Monday. And notice that that's true. So it turns out that there's a connection between the two true statements as well as the two false statements. So if I'm focusing on the true ones here, 1 and 4, or maybe let me phrase this a little bit differently. Let's say 4 is what we call the contrapositive of 1. And they're always equivalent. So this idea of if A implies B, we're able to say that not B implies not A. So let's think about this in relation to what we looked at above. So going back to series, what we can think of that we looked at in the prior part here is, let's assume that A is now knowing that the series converges, and B is the statement, the limit of the terms of that series is 0. We proved if A, then B. And my aside above is supposed to point out then that now we also know that the contrapositive is true, meaning if not B, then not A. So if I want to sum up that statement, not B basically implies not A. This is what we call the test for divergence. And the statement of this is if the limit as k approaches infinity of a sub k is not 0, then the series sum from k equals 1 to infinity of a sub k does not converge, which we would say diverges. So importantly, this is stated differently than what we saw above. But like I said, the statement that we're ending with is the contrapositive of the one above. And because we proved that the one above is true, its contrapositive must be true as well. The other thing I'll point out is that this is also sometimes referred to as the nth term test. But I want to emphasize that I like the name test for divergence because that makes it very clear that you can never use this test to show that something converges. It's only going to be showing us that something diverges, or we can say that it's inconclusive, and we're going to develop many other tests. And we'll see that if the terms approach 0, we need to move on and use something else.